Okay, so I'm going to be showing the results for a few different simulations I ran on an axisymmetric pipe for the steam methane reforming reaction. So I'm going to start very briefly with a small overview of the geometry. So the geometry consists of two axisymmetries, so that the pipe is only a quarter of a pipe as opposed to a whole or a half pipe, with a diameter of 0.102 meters. And I believe the length, if I pull up the extrusion, is 5 meters. So the industrial version is supposed to be 13.7 meters. This one is 5 meters. So that may affect some of the results, and it may affect some of the computational power of the results, especially in terms of the mesh size. But that's something that we can look into a little bit later. So geometry is pretty straightforward, I think. It is a solid body, so I'm not entirely sure what would happen if we change that to a liquid, or I'm sorry, a fluid instead. So let's proceed from there to the mesh. So here's the mesh. I didn't do anything fancy with the mesh, just a few small things that I want to look at. So I didn't change the mesh from anything other than the initial automatically generated mesh that Fluent created. So if you look right here, the inlet and outlet mesh going along the axis of the pipe is a little bit strange. These ones over here are quite a bit larger. In general, it's just not a very good shape. And you can actually see in the results how this affects the results, because, well, I'll get into that later, but you can see later on kind of like the issues with the mesh here, but we still got pretty good results, even with a fairly unrefined mesh. It has 4 different name selections. One is the outlet, which is over here. One is the inlet, which is over here. And then the wall, which only occupies this rounded space. And then the symmetry, which is going to correspond to both that guy and that guy. So the symmetry just goes across the perpendicular axes. So yeah, straightforward again. I think that it would be a good idea to refine this more, especially perhaps increasing the amount of nodes, and then also changing the shape, perhaps. So those are a few different possibilities for future design. So now let's just move on to the setup. So this is where all the interesting stuff happens. So first I'll start with the conditions that I set it up with, and then I'll jump into the results. So obviously the energy model and the species model are on. Species model has what we've been doing this whole time, which is a mixture template with all of the necessary reactions, volumetric and wall surface reactions, and the other stuff that we haven't really changed at all. It does have the UDF that we've been using this whole time, and it has the function hooked to the surface reaction rate. So going on to the materials, obviously we have our typical mixture setup here. So nothing odd about that. In terms of the boundary conditions, let me see here. So looking at the inlet, I'm sorry, that was the inlet. So we set it as a velocity inlet with 0.1 meters per second for the velocity magnitude, and an inlet gauge pressure of 25 bar, which is around where the papers tend to suggest the steam methane reforming reaction should be. So for this particular one that you see here, I set the inlet temperature at 700 degrees Kelvin, but you can really change this quite a bit, and the results have been very consistent. I think maybe a few odd things, but I'll get into that in a second. For the species mole fractions, I started out with 0.234 for the water, 0.691 for the nitrogen, and 0.075 for the methane, and 0 for the rest. I think that these might be able to be varied. We might want to tinker with that a little bit in the future. But I think first we should probably establish that we can get consistent results with the industrial pipe whatsoever, and then perhaps change the mole fractions, inlet temperature, and the velocity magnitude. Okay, so moving on to the outlet. So this is set as a pressure outlet. I set the pressure outlet also to 25 bar. I noticed that this is pretty important. If I didn't set it to 25 bar, it would the pressure outline or the pressure graphs and contours would just be constant at 1 atmosphere. And I set the backflow total temperature at 1,173 Kelvin. I don't know if this matters all that much. It might not. And 0 for all of the species. So I did not set a target mass flow rate. It might be interesting if we decide to change this and this in the future. So preventing reverse flow and setting a target mass flow rate might be a couple of different avenues for just figuring out what to do with the results and how to improve them. For the symmetry, I don't think that anything was special for that. Yeah, it's just a zone name. And then for the wall, I didn't change anything with the momentum. I didn't change anything with the species. But for the thermal conditions, and I think that this is probably really important and another place that we could refine, I set the temperature to 1,173 degrees Kelvin, which is supposed, around the temperature that these things tend to operate at. And then I set it for a shell conduction with 1 layer and a thickness of 0.02 meters. So this is one thing that we might want to look into changing. I mean, the wall thickness is something that we could easily find online. I didn't do anything for the heat generation rate. I don't think that we have to, because I don't know that it's generating heat so much as it is just transferring heat. But we might want to look into some of these differences here. But yeah, so this is actually, I think, pretty important to keep in mind, having shell conduction with 1 layer and some level of thickness that is not 0. So apply, close. Okay, so that should be it in terms of the conditions. I didn't do anything fancy with the quote unquote solid. It's just set for a reaction. Yeah, we already went over all of those, so nothing to worry about. Right, so let's go to the results now. So initialization, I was able to get consistent results using both hybrid and standard initialization. Standard initialization would be from the inlet. So yeah, obviously everything would be displayed like that. And then these were run with 1,000 iterations. Everything that was the only thing I changed. I didn't change the reporting interval or any of that stuff. So, okay, so let's move on to the plots. Yeah, so I think let's just start with the temperature one over here. So this right here, I think is super, super helpful. It matches the plots for a paper that we looked at a while ago, at least fairly well. So the symmetry starts out at some value, which is much, much lower than the value of the wall. And it should be starting, I think, at the inlet temperature. So I'm a little bit confused as to why it starts so low. But it does tend to dip down to a minimum and then kind of like increase over time. So that corresponds with the reaction, which is endothermic, sucking in a bunch of heat from the environment and reducing the temperature of the system, and then increasing to approach the wall temperature. So I think that if we were to expand this to 13.7 meters, we would probably just see this continually approach this line up here. Now, the only thing that I'm a little bit concerned about with the temperature profile or graph is that the wall temperature was set at 1173 Kelvin. But here you could see that it's somewhere between 900 and 1000 Kelvin. So like, I don't know, around 940 or so. I don't know if that's of particular concern or what that's about, but I find that kind of interesting. The temperature of the wall. So this is not the fluid. This is not the reacting temperature. Obviously it drops down and then it kind of like increases. I would expect this to drop a little bit more potentially, but I think that these two guys look quite good and tend to match the literature. The minimum temperature drops down pretty low, almost to room temperature. So I'm not sure if that should be an area of concern or not. Or I'm not even sure if this is something that we could change by changing the inlet temperature or the wall temperature, just considering how endothermic the reaction is. But I did find that changing the velocity drastically changed the temperature graph. So moving on to the pressure is constant, so that's good. I imagine there's probably some change in reality. For the velocity, I thought this was kind of interesting. This pattern consistently showed up where it would start at some value and then it would have a little bit of a lower section and then it would jump up, to some level higher. So again, the velocity was set at 0.1 meters per second. The actual values increased beyond that, which I think makes sense because you're increasing the amount of moles in the system and the temperature changes along the entire system, which causes the gas to expand, increasing the volumetric flow rate and therefore the velocity. So I think that makes sense, even though the velocity starts out at 0.1, for it to double, almost triple in value. I think that does make sense, especially considering how many moles we're gaining by producing 3 hydrogen for every reaction. For the water, so this is where things get a little bit iffy, is looking at the mole fraction values, but this one actually looks better than other ones that I did, which were mostly based off of changing the velocity and the temperature. So this one is at a relatively lower temperature and lower velocity than simulations I had done previously. In previous simulations, the mole fractions tended to just start at some value way different from what I set them at. But this one actually starts, like the mole fraction that I set it at was initially, I think, 0.24. So that's really close to what we see right here. And then it drops down and then keeps dropping. I'm not really sure exactly why there would be any mole fraction at the wall, but there is. But if we were to just look at the symmetry, it looks like this. I think that's pretty reasonable. We can probably analyze this a little bit more in the future. And then looking at hydrogen, again, it starts out really, really close to 0, which is what we set it at. And so this is, again, I think it's pretty reasonable that it would jump up quite a bit within the first meter or so. And then jump up way, way up there. Considering how much hydrogen is produced in the first reaction, which I think is 3 to 1. It's possible that this is a little bit odd, but again, I think we'd have to analyze that a bit. Personally, I think it's pretty reasonable. For methane, let's get rid of the wall. Yeah, this is really similar to the water one. So starts at around the initial value, which was 0.075. Actually a little bit below it, so that implies that the reaction is already starting the instant it gets to the inlet, but it does decrease gradually, and so we don't see the issue that we had earlier, which was basically just this instantaneous reaction that showed no rate of change. It just started at a value and would go from that value. So this is pretty good, I think. Carbon monoxide, this seems pretty reasonable. The mole fraction is less than that of methane, for the most part. It never increases to being above methane, so that seems pretty good. I would expect there to be less carbon monoxide in the end, though, than what we are seeing, just because it's being consumed in the second reaction. So let's get rid of those guys again. So For carbon dioxide, it's pretty similar. I think this kind of implies that reaction 2 is not happening very quickly. It's lower than the concentration of carbon monoxide. So I think that that's important to consider. And I do think that that's consistent with these plots that I'll show in a second. For nitrogen, this isn't very important, but it does drop, the molar fraction of nitrogen drops a lot. It drops to a little bit less than half of its original value. Again, with the amount of hydrogen that's being produced, I think this is pretty consistent. For the density, this makes sense. I think it should be kind of the inverse of the temperature profiles, I would think, because this corresponds to the temperature drop in the beginning. It should increase, and then it should drop off as the temperature approaches the highest value. So yeah, so I think that that's a very useful way to verify that what we're getting is interesting and consistent. Okay, so this is the reaction rate of the first reaction that produces 3 hydrogen. The only thing is, I'm not really sure what to say about this. It seems, give me just a second. Hello? I'm not sure what the reaction rates graph is supposed to look like, but this seems pretty reasonable. The only thing is the magnitude is very high. I'm not entirely sure how to analyze this for the system though, because well, when it says that there's what 60,000 kilomoles per cubic meter per second or something like that, that seems like a very high reaction rate. I don't know what's reasonable for this particular reaction. So that's something to look at. And then comparing that to the second reaction, which is producing 1 hydrogen. So I think the most important thing to look at is that the magnitude of the second reaction is about 2 orders of magnitude, 1 to 2 orders of magnitude less than the first reaction. Actually 2 to 3 in this particular case. Again, that's something I don't know what's reasonable. I don't know what exactly makes sense. One thing I think that's kind of interesting is that they have around the same shape. In previous experiments, I had gotten them to have the opposite shape. So one looked kind of like that and one looked kind of like that. But yeah, so let's look at the contours very briefly. Right, so this is the velocity contour. I think it makes quite a bit of sense. It's also my favorite looking one, I think. Pressure one makes sense, it's just constant. Velocity contour, it makes sense because there is, so this one does not have the wall being shown. We would expect the maximum velocity to be towards the middle of the pipe and slower towards the outer part of the pipe because of the no slip condition. So I'm not really sure what to make of the mole fraction ones, but they seem consistent with the graphs, so nothing too concerning. Reaction 1, that's what that looks like. Reaction 2, that's what that looks like. They look pretty similar again. Obviously different orders of magnitude. This is carbon monoxide. I think it's a little bit too orange for my taste, but yeah. hydrogen one is a little bit odd. One thing that I actually noticed about a lot of these contours, I don't know if this is a problem or not, is that it tends to be darker towards, whatever we drew a line from like the axis to and bisected this angle 45 degrees. For some reason, it's very dark around there, implying that there's lower values in this particular section towards the wall of the pipe. I think that's probably because of the mesh design. So that's kind of what I was talking about earlier. There's that weird part in the middle of the mesh. So I think that if we refine the mesh, this would disappear and it would be more consistent along that side. So yeah, I think these make a good amount of sense. The best thing that we could do, I think, is kind of proceed from here and then see if we could set up a longer pipe with a better mesh. So first thing I think we should do is try to make the mesh better and then make the pipe longer. So yeah.